expanding on the idea of growth and decay, because what we looked at yesterday was a very simple model. So let's improve it a bit to take into account some other conditions. And the classic one is when we're talking about things cooling or heating. Right? So the temperature of an object could never drop lower than the temperature of the room, or if you're heating up, could never rise above it, and so on. We need to change our equation, and the differential equation now becomes that. It now takes into account this external condition. Now, the solution to this one, again, there is a trivial solution. In this case, the trivial solution would be that P equals N, because if you think about that one, differentiate N, you would get 0. If you substitute N into our derivative here, you would get 0. It is a solution, but again, it's a trivial solution. That's not one we're interested in. The solution we're interested in is this one, which is very similar to the solution for our basic one. It's just now we've added N. So if you think about the picture of the graph, the one we had yesterday was just the AE to the KT, a basic exponential curve. So what have we done to our curve? Well, we've shifted it up N. So that horizontal asymptote will no longer be the axis. It'll be y equals n, or p equals n in this case. That makes sense, because what we're saying up here is it could never drop lower than the temperature. That would become the horizontal asymptote. And that's really the only difference to our problem. No, P is still going to represent the population. Okay, the initial population is no longer just A, because when we substitute T equals 0 into that, we'll get N plus A. So the initial population will be N plus A. K is still our growth or decay constant, and T, of course, still represents time. Let's just have a look at this old question to have a look at how it changes the problem. So T is our temperature inside a room. A is our constant outside temperature. Newton's law of cooling. Newton did so many wonderful things for us. This is one of them. His law of cooling states the rate of change of temperature is proportional to T minus A. Starts off similar to the other ones. Show that this will satisfy the law of cooling, or the differential equation that it comes from. Okay. So T equals A plus CE to the KT. Differentiate that, we get KC e to the KT. But I can have a look at this solution that we're trying to show and notice, well, hang on a sec. CE to the KT, that's T minus A. Therefore, there's my derivative, and that's what we're trying to prove, that the rate of change is directly proportional to T minus A. And that's what our equation is saying. So, yep. It does satisfy Newton's law of cooling. We're now told that that outside air temperature is 5 degrees Celsius. But a heating system breaks down. It was set at 20 degrees, but in half an hour that's dropped to 17 degrees. How long will it take to drop to 10 degrees? The solution now becomes 5 plus CE to the KT. Remember, the external condition now is that 5 degrees. So I know that's going to be the, what do we call it? We called it N, didn't we? That's going to be the N in the problem. Yes, 5 plus C will end up being 20, the initial temperature. So C is 15. I've got my equation. Oh, I still need to work out K. We haven't got the rate of change yet. But I've got some information that will help that as well. We know after half an hour, so 0.5, T17, substitute that in, exponential equation. We've now got an expression for K. I'm not going to bother working out the decimal approximation. I'll keep it as an exact value. I can store the number in my calculator to use in the next step. We want to know when is that temperature going to be 10. Solving this one. So 1 on K, log a third. Now we can go to our calculators and we get 2.46. So it said after how many hours. I've said 2.5 because 2.46, it's almost 2.5. But again, it's that situation of make sure you write down your decimal approximation so that your conclusion makes sense. I could have said after 3 hours to the nearest hour, I suppose. Or is it to the nearest hour because it's 0.46, there's that problem. And that's why for this one I thought, 2.5 is probably a better way to answer this question. I guess the main thing is we got the 2.46. If we can show them we got that, we're going to be happy. So 16C now plays with this variation to the growth and decay model.